Welcome to This Explainer. Today, we're doing a deep dive into the fascinating physics and material science of conductive polymers. We're going to methodically deconstruct exactly how these materials work, right down to the quantum level.
Our roadmap today takes a bottom-up approach. We'll briefly cover 1. The insulation problem, 2. Conjugation and band theory, 3. Doping and charge carriers, 4. Key conductive polymers, and finally, 5 advanced technical applications. Let's get right into it.
Section 1. The insulation problem, breaking the 5 EV barrier.
So, what exactly are conductive polymers? Basically, they are organic macromolecules that can actually conduct electricity, thanks to conjugated pi electron systems. They represent a really unique hybrid class of materials, effectively bridging the gap between everyday, flexible plastics and the high-tech properties we usually associate with rigid semiconductors and metals.
Now, you might be wondering why conventional plastics act as insulators in the first place. Well, it comes down to localized sigma bonds. Because electrons are locked in place, it creates a massive energetic barrier, a band gap larger than 5 electron volts. That's just way too wide for electrons to jump. Conductive polymers, on the other hand, hack this system using delocalized pi electrons, which dramatically shrinks that energetic gap.
Moving to Section 2, Conjugation and Band Theory, the Molecular Orbital Perspective.
The absolute structural foundation of these materials is a heavily conjugated system. You literally have to have strictly alternating single and double bonds running all the way along the carbon backbone of the polymer. This exact geometry is the mandatory prerequisite for everything we're about to discuss.
Because of those strictly alternating bonds, the unhybridized p orbitals on adjacent atoms physically overlap with one another. And quantum mechanically speaking, this overlap creates highly extended, delocalized electronic states. The electrons aren't confined to a single atom anymore, they're suddenly shared across an extended network.
And here is where the real magic happens. Across really long macroscopic polymer chains, the bonding pi orbitals and antibonding pi star orbitals stack up so tightly that they merge into continuous valence and conduction bands. This successfully compresses that massive 5 EV band gap down into a highly narrow semiconductive gap. This quantum phenomenon is the exact reason why a plastic can suddenly start behaving like a metal.
That brings us to Section 3, Doping and Charge Carriers, Polarons and Bipolarons.
Okay, so we've got a narrow band gap. But to really get the current flowing, the polymer still needs a mechanism to introduce free charge carriers. We do this through a process called doping. We dramatically increase conductivity by either extracting electrons from the polymer backbone using oxidative, p-type doping, or by injecting electrons into it via reductive, n-type doping.
Crucially, charge transport here doesn't work like the free-flowing electrons in a standard copper wire. When we dope the polymer, it actually induces distinct, localized distortions in the physical lattice. The electrical charge physically couples with these structural deformations to create quasi-particles. We call these polarons, or at higher doping levels, bipolarons. It's actually these polarons and bipolarons that move and carry the charge through the polymer network.
Section 4, Key Conductive Polymers, Material Evolution. Let's look at how these materials have evolved over time.
This entire field was completely revolutionized back in 1977 when scientists discovered high conductivity in chemically doped polyacetylene. It was an absolutely astonishing academic breakthrough, and it ultimately earned the researchers the Nobel Prize in Chemistry in the year 2000.
Now, polyacetylene was amazing on paper. As the very first conductive polymer, it offered incredibly high baseline conductivity once it was doped, but it had a fatal flaw. It was terribly unstable. Expose it to normal atmospheric oxygen or moisture, and it degraded almost immediately. So outside of a controlled lab environment, it was fundamentally limited.
That severe environmental instability is what drove chemical engineers to develop polyaniline, or PANI for short. PANI basically solves the stability problem. It's highly resilient in the environment, cheap to produce, and features highly tunable oxidation states. Those characteristics make it incredibly useful for commercial sensors, anti-static coatings, and energy storage systems.
Rounding out our primary triad of materials is polypyrrole, or PP.
PP has great conductivity, but it stands out because of its exceptional biocompatibility, making it the premier choice for neural interfaces and implantable biomedical devices. And I have to mention PEDOT, PSS, a transparent, super stable polymer mixture that has effectively become the absolute industry standard for modern flexible electronics.
Finally, Section 5, Advanced Technical Applications, the future of electronics.
The unique physical properties dictated by these conjugated structures are translating directly into next-generation tech. By exploiting their lightweight, flexible, and solution-processable nature, engineers are deploying these polymers into organic photovoltaics, dynamic OLED displays, and highly stretchable wearable electronics. Because they can literally bend without breaking their conjugated pathways, they are the absolute foundation of sophisticated biosensors and flexible supercapacitors.
But challenges still remain. We're still fighting against environmental degradation, and the raw conductivity is still generally lower than pure metals. As researchers continue to rigorously refine these molecular structures to improve those baselines, we're left to wonder, once we overcome these final material constraints, how will this completely redefine the future of fully flexible, self-healing electronics? Thank you so much for joining me for this explainer.